Okay, AtCoder's beginner contest 180. Let's have a look at 4 of the problems. First one, very easy. So the problem statement, we've removed A balls from a box that contained N balls and then put B new balls into that box. How many balls does the box contain now? Well, if you start with N and then subtract A and add B, that's how many it contains. We've got some constraints here that are of no particular interest other than, I guess, the fact that we'll never end up with a negative number of balls, which I suppose is important. So the initial number of balls is between 100 and 200 inclusive. And then the number of balls that you take away is at most 100. So you can never take away more than you had to start with. So it's meant to be a very easy problem. So the input is given as 3 numbers, N, A, B. We just read 3 integers on a line. Here's an example. Right, so we read those 3 integers and then do 100 minus 1 plus 2, and that gives us 101, which is the answer. So what does this look like in Python? Well, pretty simple really. N, A, B equals int x for x in input split, and then answer equals n minus a plus b, and print answer. Okay, so you can try typing that in and submitting it. Remember, this is AtCoder's Beginners Competition 180. So if you're not familiar with it, you can go to atcoders.jp and just look back through the recent announcements until you find Beginners Contest 180. If you log in, give yourself a username, etc., then you can go to that and you can do, you can just click on tasks and go to this task and you can submit. You don't have to be running a virtual competition or anything. You can submit to a task anytime. Question B, various distances. So given is a point x1 to xn in an n-dimensional space. That sounds very confusing, and I won't get too distracted by the mathematics here. We're finding 3 distances. Now, when we talk about the distance from the point A to the point B, that's called the Euclidean distance, and it's based on Pythagoras' theorem, right? The idea of getting a diagonal distance, you can get that as the hypotenuse of a triangle. So that's called the Euclidean distance, and that's the formula there. But what I've shown you here is in 2 dimensions, but if it could be in 3, 4, 5, 6, whatever. So anyway, there's a formula there. And the Manhattan distance, here's the first one. Manhattan is in New York, and it's got a grid of streets. And so the idea is that if you wanted to get from A to B in New York, well, you kind of have to go like that and then like that. You can't go diagonally. And so the Manhattan distance is just adding that distance and that distance, right? Now, the thing is, if it was going the other way, if x2 was negative, you still want to add a positive thing. So that's why they have absolute values on them. And the Chebyshev distance, I've no idea what that is, but that is the maximum of all these absolute values. So anyway, just as a computational exercise, we're given n values. So we're told, here's the way the input's given, right? So we're told n. So let's say n was 13, then the next line would have 13 numbers on it, which I think are integers. Yes, it says here all all values in the input are integers. So we've got, let's say, I'll make up a sample input here that's more interesting than the one we're given. Let's say we're given 5 and our values are 8, -2, 3, 1, and -13. Okay, so what we then need to calculate, if we look at the Manhattan distance, so I'll call that Manhattan, well, that is the absolute value of 8 plus the absolute value of -2 plus the absolute value of 3 plus the absolute value of 1 plus the absolute value of -13. The Euclidean distance is the square root of 8 squared plus -2 squared plus 3 squared plus 1 squared plus -13 squared. Okay, now the formula uses mentions absolute values, but we don't need them because we're squaring anyway. And then the Chebyshev distance is the maximum of absolute value of 8, absolute value of -2, absolute value of 3, absolute value of 1, and absolute value of -13. So this is going to be 13. The others, I mean, this one's easy enough to add up. 13 plus 1 is 14, plus 3 is 17, plus 2 is 19, plus 8 is 27. Right? And this one, the Euclidean distance, well, I can't do that in my head. So with a better example, see, sample input 1 only has 2 input values. You can't get much of an idea from that. So I've shown you what the input could look like and then what our calculations would look like. But it was possible for me to write out these calculations because I know exactly what I'm dealing with, but our program has to deal with any value of n. So this is what the program could look like. So n equals int input. Okay, so that could be like our 5. And then we've got we've got x1, x2 up to xn, right? Well, I'll just say capital X is int little x for x in input split. Okay, and that could be our 8, -2, 3, 3, 1, and -13. And of course, if that's what it looks like, then like in the input, then by the time this bit of code's done with it, then we'll have a list where they're actually integers. Okay, and so now we're going to go through the list exactly once and build up what we need as we go. So let's start with the set our answers all to 0. So we can have the Manhattan, the Euclidean, and the Chebyshev distance is all 0, 0, 0. And then we can say for little x in big X, sorry if you find that confusing, but big X is our list of things, and then little x will be each individual thing. Okay, so we'll have x will be 8, and then when we're done with that, x will be -2, and then when we're done with that, x will be 3, and so on. Right, so what do we do? Well, the Manhattan distance, we just have to add the absolute value of little x. Okay, we just keep adding it to the Manhattan distance. The Euclidean distance, well, we're going to we're going to just add the square of x, and then at the end we'll take the square root. And the Chebyshev distance, well, that's the maximum of them. So I'm going to say Chebyshev equals the maximum of Chebyshev and the current, the absolute value. So as we go through, by the end of the list, the Chebyshev will be the maximum of all of them. The Euclidean will be the sum of the squares, which we have to square root, and the Manhattan will be the correct answer. And so now we just say Euclidean equals math dot square root Euclidean. Right, and for that to work, we need import math up the top. And so now we print on 3 separate lines. So I'll say print Manhattan, print Euclidean, and print Chebyshev. All right, so that's that for problem B. Feel free to give that a go. Problem C, cream puff. We have n cream puffs. Find the possible number of people to which we can evenly distribute the cream puffs without cutting them. It's just finding all the factors. Finding all the factors of a number is pretty easy, but look how big the number can be. That's 1 trillion. So if the input was 6, then the output is 1, 2, 3, 6. If the input was 720, then we get a lot of output. And then for this big number, clearly it's prime because our factors are 1 and itself only. All right, so what we're being asked to do is very simple. Problem is, just like the obvious thing to do when getting the factors of a number is to query every number from 1 to n. So here's a really simple approach. N equals int input, so that's the only input there is. So we get that. And then let's say for A in range, right, and we'll go from 1 to n inclusive, so I have to do n plus 1. If capital N mod A is 0, then that means n is a factor. It means A is a factor. Print A. Okay, so that is a correct implementation for this problem. There's only one problem. If n is 10 to the 12, then this runs 10 to the 12 times. Now, that's too much. That's way too much for the computer because 10 to the 12 is a really, really large number. We have no right to ask a computer to do something 10 to the 12 times. Just as a rough idea, we've got 2 seconds here, and a computer can do about 10 to the 9 things per second. So we're very far short of being able to do 10 to the 12 things. And this is speaking very roughly because we've got no idea of how long a single thing takes. But just speaking very roughly, and that's very important to get an idea of whether it's reasonable to ask a computer whether it's reasonable request for the computer. So anyway, think of the number like 20. So the answer is 1, 2, 3, no, not 3, 1, 2, 4, 5, 10, and 20. And you'll notice that there's a big gulf here, right? We only need to go up to the halfway point because there's no point asking about 11, 12 and all that. They're too big. So we could have another approach, okay, and say for A in range, right, starting at 1. Now, how do we go to the halfway point? Because the number might be odd. So what I'm going to do is I'm just going to do n plus 1 divide by 2. Double divide in Python to get an integer division. So if n is 20, then n plus 1 over 2 is 21 over 2, which is 10. And if n was, say, 21, then 21 plus 1 over 2 is 11, and that's it's about halfway. The thing is, it's guaranteed not to miss the halfway point. Okay, and then we've got exactly the same thing here. But then, at the end, we need to print n itself. Okay, so what about this? We've halved the work. Now, halving the work sounds great. If you have a job to do yourself and you can find a way to halve the work, then you'll feel pretty good about that. But what about a computer? So once again, let's say n is 10 to the 12, then how much work are we doing in this loop? We're doing half of 10 to the 12. Now, if you divide 10 to the 12 by 2, then that is 5 times 10 to the 11. So we're doing on the order of 10 to the 11 things here. And that's still far too much, isn't it? So here's an important lesson for you. If you're asking the computer to do too much, and then you find a way of only doing half as much, it's almost guaranteed that you're still doing far too much. So what we need to do is realise, I'm sure most of you would already realise this, that when you're looking for factors of a number, you only need to go up to the square root. So let's consider 20 again. So we got 1, 2, 4, 5, 10, and 20. 21. 1, 3, 7, 21. 22 is 1, 2, 11, 22. 23 is 1 and 23. 24. 1, 2, 3, 4, 6, 8, 12, 24. And finally 25. 1, 5, 25. So by considering a few different inputs, I've got a nice range here. We've got a prime number. I've got a heavily complex number in 24, and importantly, I've got a square number. So I'm going to mark in where the square root is here. So with 20, the square root's between 4 and 5. With 21, it's between 3 and 7. 22, it's here, here. 24 is nearly 25, so the square root's nearly 5. And 25, the square root is 5, right? So now what we've got is if in every case except the last one, we cut the factors perfectly in half, right? And so basically we can see factor pairs, and that's nothing new to you. The idea that when we look at 20, you can look at factor pairs, right? 1 and 20, 2 and 10, 4 and 5, and we're done. Okay, but how do we know when to stop? Well, the lesser known fact is that the square root of the number tells you where to stop. 23. You've got 1 and 23. What's the square root of 23? 4 point something. So we'll stop at 4. 2 doesn't go into it. 3 doesn't go into it. 4 doesn't go into it. Now we stop. We've got all the factors. 24. 1 and 20. Okay, the square root is nearly 5, but it's not 5, right? We'll stop at 4. Or we could stop at 5. I don't care. 1 and 24. 2 and 12. 3 and 8. 4 and 6. Well, let's say we'll stop at 5 to be safe. 5 and, well, doesn't go, and we stop. And we've got all the factors of 24, right? Now, in a program, what do we do? Because we need to print them out in order. Here's what we do. We start a list of factors, and as we go through, we just keep adding to the list. Okay, and that's our final list. But we need to print them out in order. So if I call it capital F for factors, all I need to do is do f.sort, right? And then for A in F, print A. Done. So we can build the list not in order, and then we ask the computer to sort it. We don't have to do any work for that. The computer can do that quite quickly, and then we print them one at a time. So what about 25? What about a number that's actually a square number? We need to treat that a little bit more carefully, because we don't want to end up with that. We're not allowed to print the 5 twice. So what can we do? Well, first of all, we might as well calculate where we're going to stop. And so whatever our number is, I like to maybe calculate the maximum factor that we're going to try. And if we were to say math.square root of n, then if n was 24, then we'd get, say, 4.89 or something like that. ... And if n was 25, we'd get 5.0. Now, if we run that through the ceiling function, then in both cases we'll get an integer 5. So if we calculate the ceiling of the square root of n, then that means we'll get an integer that we can work with in a range, and that can be our stopping point for checking for factors. But we need to check, right? If we've got a number like 25, then what we need to check is whether the maximum is actually a factor. Then it means we have a square number. Or maybe I'll say if the maximum times the maximum is equal to n, then we have a square number which we treat carefully. Otherwise, we have a non-square number. All right? Okay, let's get a complete program going here. So, of course, we have n equals input, and we'll import math, and we'll say max equals math dot ceiling math dot square root n. Okay, now we'll say if max times max equals n, we need a list of factors, empty list. If max times max equals n, first of all, I'm just going to, I don't want to fiddle around with really small numbers. Okay, so I'm doing a specific answer for very small numbers, 1, 2, and 3. And, right. And now we'll get into, okay, I don't need an else because if we hit one of those, we exit. So now let's just get on with it. Okay, so if max times max is n, then we have a square number that we have to be careful of. And I'm going to be careful in the following way. I'm going to start off my factors. Okay, I don't have the factors yet, do I? Right. Let's start my factors with the number 1 and n. And then if I have a square number, then I'll go f dot append max. Right, so we've put the square root in. So if n was 25, we've just put in 5, and we've got 1, 5, and 25. If n was 100, then we've got 1 and 100 and 10. Okay, and so now what I'm going to do is say for a in range. Now, what do we want our range to be? We're not starting at 1 because I've already put 1 in the factor list, so we're starting at 2. And I'm going to go up to, but not including the max, because if max is a factor, I've already dealt with that. So I don't want to include it again. So now if n mod a is 0, so if we have a factor, what do? We go f dot append a, and we also put in its factor pair, f dot append n double divide a. Right, that goes through all the factors that we need. And now we can just go f dot sort, and then for a in f, print a, and that's our complete program. So you might like to try typing all that in and try it with some values yourself, like 720, and check that you get all the numbers you see here. Try some square numbers, try some small ones, some large ones. Now let's think about whether we're asking the computer to do a reasonable amount of work. So if n is our worst case, 10 to the 12, here's where all the work gets done. So for A in range then the max in this case is going to be 10 to the 6. So the square root. And so we'd be doing 10 to the 6 times. Now I said that, well, I don't remember exactly what I said, but in rough terms, we can ask a computer to do about 10 to the 8 things per second. So we're covered here. We're doing simple things up to 10 to the 6 times. So this will work. All right, so give that a go. Finally, question D. More complicated, but it's not too bad. So we've got a complex story. So Iroha is into a game where you keep pets. Iroha's pet is Takahashi. Initially, Takahashi's STR and EXP, so 2 variables, I imagine they stand for strength and experience or something, are X and 0 respectively. These parameters increase in the following 2 kinds of training. If you go to one gym, then you multiply the first variable by A and you add 1 to the second. If you go to the other kind of gym, then you add B and increase that. So no matter what, this goes up by 1 every time. The choice is, if you go to the gym, you multiply it by one number or you add another number. Takahashi evolves when his strength becomes Y or greater, but Iroha thinks that makes him look less cute. So find the maximum possible EXP when he is trained without letting him evolve. Okay, so question like this, you need to just spend a little bit of time taking it in. But you notice, like, this is the same no matter what, and this is the difference, and that you have a choice, right? And that your motivation is to keep STR low. Now we've got some pretty nasty numbers that can go in here, up to 10 to the 18. I've done my own sample input here. So I should show you you get 4 numbers, X, Y, A, and B. X is your initial value, Y is your target value. A is what you multiply by, optionally, and B is what you add, optionally. So just for the sake of getting on with things, I've got my own sample input here. So 1 and 200 is where you start and stop. 3 is the number that you can multiply, and 20 is the number that you can add. So let's say that you only multiply. Then your chain of numbers goes 1, 3, 9, 27, 81, 243. Now 243 is greater than our target, and so we would stop at 81, and our answer, because we're counting the EXP value, that would be 1, 2, 3, 4, 5. Right? Our answer that we print out would be 5. I think that's what we print out. Yes, we print that out. Right, what if we add 20 instead? So we get 1, right, we're looking at this one, 1, 21, 41, 61, and so on. Eventually we get to 201, which is just a little bit too much. So our highest value we can get without evolving is 181. And what's our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we can get an output of 10 here. We all know that around a certain point, adding things is going to increase more slowly than multiplying things. But what you can see here is that the adding, well, it gets to 21, 41 very quickly, whereas the multiplying takes a bit more time to get going. But once it's going, it's really going. But if we take the optimal approach, then we multiply. 1, 3, 9, 27. That's all multiplying. And now we switch to adding. And once we switch to adding, we never again go back to multiplying. That's the secret to this problem. Okay? We never switch again to multiplying. So, but the question is, at what point should we switch to adding? Well, reasonably simple to say. At each point, well, think about this first of all. If we had multiplied, that would have been 81, which is bigger than the 47 we can get from adding, right? So because the 47 is the smaller value, we take that. And as soon as we take one that's adding, then we just keep adding. We don't need to do any more checking. And so let's sort of play it out here a bit with a kind of a tree. So if we start with 1, then multiplying gets 3 and adding gets 21. Which one of those do we want to take? We want to take that one, okay? We don't consider the 21 anymore. Starting with 3, if we multiply, we get 9. If we add, we get 23. Which of those do we want to take? Well, we want to take that. Starting with 9, get 27 or 29. I've already circled the 27. That's what we want to take. Starting with 27, if we multiply, we'll get 81. And if we add, we'll get 47. And hello, now we're taking an add instead. And that means we don't ever need to consider multiplying again. So we've got 67, 87, and so on, up to 207, which is a bit too much. And so, yeah. All the while, we're keeping track, I'm using purple here, of our EXP value, our experience. So 1, 2, 3, 4, 5, 6, 7, ... Okay, and we end up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right? Or we'd get to 13 and then we go, oh, but that's one too many. So we'll just subtract 1 and print that as the answer. Now, I want you to think of a bit of a, what if I gave you the following input? 1 and 1, an enormous number, and then you can multiply by 5 or you can add 10. Now, if I play out the tree a little bit, start at 1, you can either multiply by 5 or you can add 10. All right, we'll take that. Okay, you can multiply by 5 or you can add 10. Okay, and adding is the better thing to do here. Can't seem to write. Okay, well, my software has a problem. I can't write anymore. So I'll just quickly say we get 1, 5, and then 15, 25, 35, and so on. But if you actually count every number on the way up to the target, then you're doing too much work. And so you need to work out how many steps there will be by adding, by using division, instead of actually doing all that counting. Okay, so you can have a go of implementing that yourself if you like. And good luck.